selection sort. Selection sort is somewhat similar to bubble sort, but unlike bubble sort, there are no intermediate swaps that keep happening in selection sort. Of course, we compare each element with each and every other element, but we don't do swappings unnecessarily. Like for instance, here I compare 5 with 4, swap, 5 with 3, swap, 5 with 2, swap, 5 with 1, swap, which is not necessary. Only if I would have swapped 5 with 1, that would be sufficient enough, right? That's enough. Why we had to swap 5 with 4, again 5 with 3, again 5 with 2, again 5 with 1? No, not required, right? Conventionally, what we do in bubble sort is we take the largest element and we push it to the last. Next largest element, push it to the last. But conventionally, what we do in selection sort is we take the smallest element and then we push it to the first place. We bring it to the first place, and then we take the next smallest element and we bring it to the second place, and so on. So if we talk about the code, how would the code work? Of course, there are two for loops because we have to compare each element with each and every other element. So therefore, the outer loop signifies the number of times the sorting has to happen. As I told in bubble sort, the number of times sorting has to happen is the number of elements which are present. How many elements are present? 10 elements. So therefore, I have to sort 10 times, right? So, I mean, I don't have to sort n times, but at least I have to run the loop n times because I have to compare each element with each and every other element. That is, what I'm meaning to say is we have to place n elements in their proper positions. But you only notice that if n minus 1 elements are placed in their proper positions, there's no need for me to place the last element because it will automatically be there in its own position. Right. Therefore, I have to sort n minus 1 elements. If I were to write this in a loop, and starting from I is equal to 1, I would write I is equal to 1, I is less than or equal to n minus 1 I plus plus. But if we follow zero based indexing in arrays, which most of the programming languages do, it would be easier for me if I write I is equal to 0 to n minus 2. That is, I reduced 1 here also, here also. So yeah, now this is about it. I is equal to 0 to I, and this is the number of elements I have to sort. Now if we write about the inner logic states that, okay, whichever element currently I am concerned with is nothing but I. Let me assume that is the smallest element. But let me see if there is any other element smaller than the current element to its right, if there is any other element. Why to its right and why not to its left? Because the elements which are to its left will already be sorted because I take the smallest element and I place it in the front. So therefore, the elements will be which are at the left are already the smaller elements. I don't have to compare with them because they are already small. I know that. So therefore, I'll compare only with the next elements. Which are the next elements? The elements that are there on my right. Which are those elements? J is equal to I plus 1. J less than or equal to n minus 1 because the last index is n minus 1 and j plus plus. So therefore, what I do now is I have to compare this min position, element at min position, with element at this j. So I compare. So I have to compare if the element at j is lesser than the element at min position, then my min position is no longer min position. My min position is j because that is where the smallest element is currently present. So that's it. Lastly, I will check if min position is not I. That means there is some other element right side of me which is smaller than me. So I'll swap only with that element. Then swap. Swap what and what? A of min position and A of I. Okay, that's it. Let me try run this code for you. Now I is equal to 0 and I've assumed that min position is equal to 0 as well. Now I start the inner loop from the right side and I see that the element at index 1, 4 is greater than me, so no change in min position. the element at 2, which is 0, is smaller than me. So therefore the min position is updated and it becomes 2. Next, the element at index 3, which is 2, is greater than the element at min position, which is 0. So therefore there is no change in min position. Next we come to the index at element at index 4, which is 1, and that is greater than the element at the min position, which is 0. 1 is greater than 0, so therefore no change. In a nutshell, what is happening here is we just are finding which is the smallest element on the right side of me. That's it. And we are storing that index in the min position value. Now initially my assumption was I is the min position, but now I see that min position is 2, which means that I have to do some swap. So I check if I or min position is not equal to I, then I swap. Okay, yeah. So therefore now I swap 3 with 0, so it becomes 4, 0, 4, 3, 2, 1. As you can see, the smallest element, which is 0, has been pushed to the left. Next, similarly, we consider here that okay, min position is, we assume that min position is 1, which is because I is equal to 1 now. And then we check to the right, we check that okay, the index at the element at index 2, which is 3, is smaller than 4, so therefore min position changes to 2. And then we check 2 with 3, and then min position changes to 3. And then we check 2 with 1, so min position changes to 1. So what happens is we swap I, which is equal to 1, element at index I, and element at index 4. The min position, sorry, the min index is equal to 4, right? Yeah, that's it. So therefore the array becomes 1, 3, 2, 4. And similarly, the process will continue for I is equal to 1, I is equal to 2, and I is equal to